Recording's rolling. It is Friday, September 26th. So I have a Kahoot lined up for you guys. A lot of you guys already signed on. The pin is on the board right behind me here. And so most of these questions are related to Newton's first law of motion. Let's go over Newton's law, and then some are kind of tangentially related. Okay? So let's hit all the laws, and then we'll jump to the Kahoot. Yeah. And if we have more time, then I'll solve more technical puzzles with the eyes, and that'll take us to the weekend. Okay, so Newton's first law of motion is also called the law of inertia. This is the one that says an object at rest will remain at rest. An object in motion will maintain its velocity, which is to say speed and also direction of motion, unless there's an external net force acting on that object. Okay. So if there's something that's either at rest and staying at rest, then you know the sum of the forces is equal to zero. Okay. Or if it's moving in a straight line at constant speed, that will be a constant velocity. That's also zero net force. Anything like that. If there is an external net force, so the forces don't zero out, then that object will be either speeding up, slowing down, or going around a curve. Right? It has to be something like that. Right? Guys, I got a picture here of Voyager spacecraft. I think this might be one of the questions that you guys about to get. So Voyager spacecraft, this was launched back in the 1970s, so about 50 years ago, and it's just going to this day. How much fuel does it need to keep going? None. Yeah, it doesn't need any fuel. Right? It's just whatever speed it's been going. It's just going now. Right? It's just coasting. Right? There's nothing really to slow it down at this point. The sun pulls on a little bit, but right. And then set these other laws. Right, so Newton's second law of motion. This one I'll tend to pull out to solve a lot of these textbook puzzles. It tells you how much something accelerates. So you take the net force, you divide by the mass of the object that net force is acting on, right, and that's how much it will accelerate. A lot of times it's written as F equals ma. Right? But this F refers to the net force. So if there's multiple forces, you sum them up first as if it's a single force. Okay. Then finally, Newton's third law of motion. This is the equal and opposite rule. So if you have two interacting objects, okay, this cannonball, this cannon, or the Earth and the moon, okay, for every active force by object A and object B, there's a reactive force equal in magnitude, opposite direction by object B back on object A. Okay? I also have Kahoots for these other ones, which we might hit next week. But yeah, we'll do this one right here. All right, and then see how much time we have left. Oh yeah, you guys are all ready to go. All right, show me okay. All right, go ahead. Galileo found that while rolling down one inclined plane would roll how far up another inclined plane? Yeah, to its original height. To its original height or nearly its original height. Okay, and I should draw that one out for you guys. Oh yeah.
We ignoring gravity. Yeah.
Oh no, gravity's part of it. Yeah, gravity's part of it. Okay. So here guys, if you have one inclined plane and then you got another inclined plane, right? So maybe like a half pipe looking type shape, right? Okay. You have a ball here, and you let it just roll down. Right? It'll roll up to probably like up to its original height, right? Or maybe like nearly its original height. If there's no friction loss. Well, what we are ignoring is friction. Right? Yeah. So if you ignore friction, if you go up to that, all right. Back to its original height. Okay. Yeah. All right, got points on the board. Oh yeah. Law of inertia states that an object will do what unless an outside force acts on it. Yeah, all those work. All those work. Yeah. Objects at rest will remain at rest. An object in motion will continue moving with the same velocity in a straight line. Yeah, all those work. Yeah, yeah. That's Newton's first law of motion. So we got Cole, Kyan, Olivia, Isabella, Spencer. Law of inertia. What does it actually apply to? Yeah, everything. Yeah, everything. Law of motion applies to everything. Cole, Kyan, Olivia, Spencer, Isabella. After a cannonball is fired into frictionless space, kind of reminds me of that Voyager spacecraft. The amount of force needed to keep it going equals. Yeah, 0 newtons, no force. Right, it's just going. Middle of deep space. Right, there's no frictional losses. There's no gravitational fields nearby. Yeah, it's just going. It's just going. Right. All right. Got Spencer, Anna, Cole, Isabella, Olivia. If the force of gravity suddenly stopped acting on the planets, here, the colors match. Which color? Right, there's a little planet right there. Suddenly gravity turns off. Which direction does it go? Ooh. Gravity suddenly turned off. Yeah, look at you guys. Yeah. And straight line tangent to its orbit. Straight line tangent to its orbit. Here, I'll draw that out on paper also. Right. So yeah, this will probably end up being a midterm question too. Okay. Right, so say you got the sun at the center, you got some planet going around, right? An orbit that oh, we're about to talk about the orbit shape in a few weeks. Does anybody know what shape it actually is? It's not quite a circle. It's actually what shape? Yeah, it's like an ellipse. Yeah, but it's pretty close to circular. A lot of times we estimate. Right. Wait, suppose it gets like right here, and the sun's pulling it maybe that way towards the sun. Okay. What if gravity turned off so there is no more gravity? It's going to continue off in that direction right there. So velocity is tangent to its orbit. Okay? That's law of inertia. Just keeps on going. Okay? Hey, would that also be true? Is what if you had a ball on a string, and this is you in the center of the circle. This is your string. Here's the ball, and you let go of the ball right here. So you just turn the tension off right here. Which way does the ball fly straight away, or does the ball keep going in the same direction it was going? Yeah, same direction it was going. Yeah, it's the same answer. Same answer. Right? You got a ball and string. You let go of the ball right here. Yeah, just keeps flying off in a straight line. That's right. Same thing. Same thing. I got Bruce, Cole, Anna, Olivia, Isabella. A sheet of paper can be withdrawn under a container of milk without toppling it if the paper is jerked quickly because, kind of reminds me of that tablecloth trick. Did I show you guys polish it with the tablecloth? I had all the dishes set up, flipped out the tablecloth, all the dishes stayed right in place. Yeah, inertia. Yeah, that carton of milk has inertia. Just wants to sit right there. Or Paul Hewitt with his all his dishes set up. All his dishes had inertia. They just want to sit right there. Yeah, that's it. Spencer, Kai, Bruce, Anna, Isabella. So 5 for the top 5. One object has twice as much mass as another object, which means it also has twice as much what? Twice the mass. That's like twice the. What's the inertia? Okay, so mass measured in kilograms, is a measure of how much inertia in a linear sense. Okay, so I'll show you guys an example. Okay, so isn't this here 500 grams and this is 1,000 grams? Okay, so this one in my right hand weighs twice as much as this one on my left and right. Okay, weighs twice as much, twice the weight, but that's not really what we're talking about. We're not talking about weight. We're talking about mass or inertia, right? So that's more like not if I pick it up, but what if I do this with it? Okay. Do I feel some resistance to change in motion? What would this feel like on the moon? Would this feel exactly the same on the moon as what I'm doing right here? Yeah, it would be identical. Like if I didn't know what planet I was on, this would not be very helpful. Right? If I picked it up, maybe that would be right, but not if I do this. It feels exactly the same. Okay, but over here, is this more difficult to do right here? Yeah, I feel more resistance to change in motion. It's twice the mass. It's twice the inertia. Okay? In fact, you get the same motion from it, would I need to apply like twice the force? Yeah. Okay. Well, if you're out in deep space, right? So we're up in the International Space Station. Everything's just floating around, floating around. Okay. And we're throwing this back and forth. Shoo, 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 shoo. And we're throwing this. Wah, wah, wah. Yeah, none of these have weight in space. Right? They're all just like floating around. Okay. But yeah, this one has twice the resistance to change in motion. It's twice the mass. Ooh, sure does. Twice the inertia. Got Anna, Spencer, Kai, Isabella, Bruce. Compared to its weight on Earth, a 10-kilogram object on the moon will weigh. We're talking about force. Weight is a force. On the moon, it weighs what? Yeah, it does weigh less on the moon. That's true. Yeah. All right. So it's lighter on the moon, easier to pick up on the moon. All right. So you guys got that. You guys got that. All right. Here's a little bit different question. Compared to its mass on Earth, the mass of a 10-kilogram object on the moon. What is that? Same mass. Yeah, same mass. All right, there you go. All right, so the mass is the same, kilograms the same. Okay, so the weight is different. That's different. Got Gavin, Anna, Spencer, Kai, Bruce. Ooh, all you guys are in the 5,000s. Ooh, this is a tight race. It's a good one. The mass of a sheep. Suppose it weighs 110 newtons. What's its mass approximately? Yeah, 11 kilograms. 11 kilograms. Here. So, remind you guys how this is working. Right, you guys remember that weight, weight, we've been calling mg, right? Mass times gravity field, something like that. Right. Here, I'll work backwards from the answer. If it was 11 kilograms mass and Earth gravity, we usually round to about 10 meters per second squared. It's like 9.8, but let's call it 10. Okay. Wouldn't that give you a weight of 110 newtons? Is that what that would be? Okay, so we got. There you go. Right. Of course, that would be on Earth, but it's the only place I know sheep are. All right, Gavin, Anna, Spencer, Bruce, Kai. A 50 Newton force and a 45 Newton force act in opposite directions. What's the net force? Yeah, 30 newtons, right, in opposite directions. Right, so right, draw this up. We got so you got some object here. We got 45 newtons one way. We got 15 newtons the other way. How they sort of subtract from each other. Okay. Now, one trick you can use is called tip-to-tail vector addition. Okay. Suppose you have this object here has 5 forces on it. You guys see 5 individual forces. Okay. So I got this here, and I'm pushing this way, and this way, and this way, and this way, and this way, pushing all different ways. Okay. Now, I can take those one at a time and connect them tip to tail. Wherever I end up from where I started, right, that would represent the resultant. In this case, it's the forces. That's the net force. It's as if there's a single force on this object that's up there. You can kind of see that from the beginning. It's like, okay, I see more kind of up and to the right than down to the left. And that's what there. And okay, so back to this one then. Right, what if I connect those tip to tail? So I got my 45 newtons to the right, 45 newtons. And then tip to tail, got 15 newtons back the other way. Okay. So my resultant, here, I'll change ink color here. The resultant would be this right here, which is 30 newtons, right? And that would get the net force. Boom. All right, you guys good? Good. All right, Gavin, hi, Anna, Spencer, Bruce. Ooh, you would have the largest mass of gold if your chunk of gold weighed 1 Newton where? All right, let's see how you. I have is that 3 winners? 3 winners? All right, so I'm drawing some scales off screen here. Drawing some scales, getting this ready. Okay. Right. The moon, or Earth, or Jupiter. Right? And why would it be the moon? Right.
Oh, never mind.
Okay. So here's my three scales. Let's go. Here's the moon. Here's the Earth. All right, and Jupiter's like huge, right? Jupiter. Okay.
Yeah.
All right, and all these scales are reading 1 Newton of weight, right? They're all reading 1 Newton of weight, right? So what does the massive goal look like on each one? Well, on the moon, I bet it would look like this. On Earth, I bet it looks like this. And on Jupiter, I bet it looks like this, right? Like something like that. Right? Because weight is mass times gravity field, right? Or if you like, mass could be weight divided by gravity field. If you like, maybe those sticks say the same thing. Okay. So they're all showing 1 Newton of weight. Okay, so 1 Newton of weight. Okay. Okay. So then, uh, for say Jupiter, if you divide by a huge gravity field, that would correspond to a small mass, right? Or vice versa for the moon, divided by a small gravity field, gives you a large mass. Or what if you think about it forwards, right? So on the moon, even a huge mass in a weak gravity field produces, say 1 Newton. Okay. But on Jupiter, a really tiny mass in a really strong gravity field can also produce 1 Newton. Okay. See after that? So it looks about like that. Yeah. So largest one. You guys got it now? Okay. I want to take some fun. Oh, got Anna, Spencer, Cole, Gavin, Bruce. Equilibrium. Equilibrium.
Uh, oh, I think I'm gonna have to follow over. You didn't choose it.
Yeah, all the above. So the net force is 0, and that's also true uh, along each axis, right? So along x-axis, y-axis, z-axis. Actually, this yellow one we haven't talked about yet. We'll bring this in January. So you guys ever like used a wrench, right? It's like some force with times some lever arm, right? That's what torque is. Right? That would also zero out. So we'll bring that in next semester. Yeah. Right. So you would need all those conditions. All right. Got Anna, Gavin, Cole, Spencer, Bruce. So this guy weighs 500 newtons. What's the tension in each strand of rope? He's hanging right at the middle. So his weight's 500 newtons. So what's the tension in each strand of rope? Yeah, 250. All right, you guys got it. Right. So 250 up, 500 down. That would zero out, wouldn't it? Right.
It doesn't matter.
Ooh, here's a trickier version of this question. Thanks an extension idea here. Right. What if I got this guy hanging here? Right. But what if he's not at the middle though? What if I extend this over this way? Okay. And there's a rope here and there's a rope here. And what if I make say a force diagram for this bar? Okay. So this guy weighs 500 newtons. 500 newtons. Okay. Give him a weight, right? Mg equals 500 newtons. Okay. Uh, do you think that these two tensions also add up to 500 newtons? Would that make sense? Yeah. Okay. So they would, so that you're making this condition. Sum of forces in the vertical direction goes to 0 newtons. That's true. Okay. But do you think they're both 250 now?
No.
You're right. It would not be. Which tension do you think is more? The one on the left or the one on the right? Yeah, this left tension right here. Okay. So this might be so many newtons, and this is so many newtons. I'll call this tension left and tension right. And yeah, they would add up to 500 up. Maybe it's like 400 and 100. Maybe it's 300 and 200. Do you think it depends where he's located? Yeah, it's like if he was right underneath this one, do you think this one would probably be pretty close to 500? This one would get pretty close to 0? Yeah, right. That makes sense. Huh. Okay, so that right now, I have not shown you guys how to solve, but hold on to that because actually, you have to go through torque to solve that. So you can't just solve that with force alone. Right? You also have to go through torque to figure out exactly what are the forces on those ropes. You have to know exactly where is he hanging. And so, yeah, we'll probably about January we'll start looking at that. I got Kai, Cole, Gavin, Spencer, Bruce. friction is a force that always acts. Yeah, opposite motion. Right, trying to slow things down. Right. You guys remember a few days ago, you were dragging weights horizontally across the surface. You were say pull into the right, and the friction would pull back to the left. Yeah, so friction's always opposite of the motion. Got Anna, Cole, Gavin, Bruce, Spencer. What is the maximum resultant possible from 3 newtons and 4 newtons? All right, yeah, everybody got it. Oh yeah. So that's in the same direction. In the same direction. Okay. Guys, how can you take 3 and 4 newtons? Can you get a 1 Newton force out of that?
Yeah.
How would you do that?
Opposite direction.
Yeah, opposite directions. How would you get a 5 Newton force out of that? Perpendicular. Actually, would that be a 3, 4, 5 triangle setup? Right? You have Pythagorean theorem. Yeah. Right. I don't think you can get 10 out of it though. All right. All right. Here you go. Yeah, I got Anna, Cole, Gavin, Bruce, Spencer. Oh, look, you guys over 10,000. Tight race. Who's gonna win? What's the tension in the? Oh, this is a good question here. Tension in the clothesline. Less than half the weight of the tire, half the weight of the tire, or more than half the weight of the tire? Hmm.
If we're talking about tension to your side, it would be half then. But.
And it's here. So how many guys? Okay, got four. Four of you guys got that. Right. Turns out more than half the weight of the tire, and I want to convince you guys that that's true. Right. So that is basically this right here, isn't it? Could this be the tire pulling straight down? Right. And then you have that clothesline doing something like this. Right. Now, actually, I start with something a little different.
Yeah.
What if what if I simplify this? What if the tire here? I'll actually draw like a tire with some weight pulling straight down. Let's say it weighs like 100 newtons or whatever. I'm just making something up. Right? What if it was supported by two? Uh, Here, change this here. What if I had the rope going pretty much vertical? Like what if it was hanging like that? Hanging like that? Now, if that was the case, what would the tension be in the rope in that case? It would be half the weight, pretty much exactly, wouldn't it? Okay. So it'd be this tension is 50 newtons. This tension is 50 newtons. Okay. So the tension in this rope actually would be half the weight of the tire in that case, wouldn't it? Is it? Okay. Okay. But when you change the angle, right, you make it more and more horizontal, that force also increases. So, do you guys remember doing that mini lab about 2 weeks ago? Right? The more horizontally you pull these spring scales, what happened to the force in the spring scales? They increased, didn't they? Or vice versa, if you pulled them harder, it would make it more horizontal, something like that. Okay? So here would be half the weight if they're both pulling straight up, and then when you pull them out, more horizontal, they get more and more and more. Yeah, so more than half the weight. That's big. All right, let's get okay. Which has more mass, a kilogram of feathers or a kilogram of iron?
That's not true.
Oh.
Yeah, same mass. They're both 1 kilogram. Both 1 kilogram. Right? Now maybe they occupy different volume. They have different densities, different volumes. But 1 kilogram, still 1 kilogram. Yeah, same mass. Oh, whoops, sorry, didn't mean to skip past the. How much does a 5 kilogram bag of bolts weigh?
Now let's do about different.
Oh, it's on Earth, right? Did you reasonably assume that you're on Earth? Yeah, so on guys, isn't that exactly opposite of the sheep question?
Oh,
Okay,
it's grand.
the sheep, you were told the weight and asked for the mass. The bag of bolts, you're told the mass and you're asked for the weight. Isn't weight equal to mg?
Yeah.
So 5 kilograms mass times about 10 meters per second squared gravity field. Yeah, it's about 50 newtons. Right, 50 newtons weight. Takes about 50 newtons of force to pick up that bag of bolts. Are you guys okay?
Yeah. Yeah.
All right, let's see. All right, so we got Anna, Gavin, Spencer, Bruce, Cole. Woo! And you guys ready for the last question? All right, here's for the win. Who's going to win Kahoot? Who's gonna win Kahoot? 50 Newton force, 20 Newton force, act in the same direction. What's the net force? Yeah, 35 newtons. Okay, so same direction, just add them up. Okay, so you guys get that too? Just add them up. All right, let's see. Podium. With the bronze, Spencer. With the silver, Bruce. And the gold, Cole. All right, nice job. Nice job. All right, so for last few minutes here, let's do a an elevator question. You guys see that elevator? Suppose you step in an elevator, and what's the elevator? Oh, you know what? I think I have a demo sort of ready to go too. All right, did I show you guys this already? Looks familiar. This guy steps in an elevator. He weighs like 200, I don't know, pounds or something.
Oh, yeah.
Okay, and the needle jumps up to 220 and then down to 180. Right. So you guys see that needle like moving around, right? Right. Actually, I think we can take advantage of that. Let's solve exactly what you guys just saw in the video. Like that could be fun. I wonder how much he was accelerating upward. Huh. Maybe like what's this acceleration here? This poster is telling you it's geared towards like what's the reading on the scale, like the normal force reading on the scale as a function of the acceleration. But maybe we'll want to go the other way because you guys saw the reading on the scale in that video. Okay. So how much was that elevator accelerating? Okay, so let's go inside this elevator here. Elevator. So a little scale right here. This guy's standing on a scale. And let's get some forces. So make a free body diagram. FBD, free body diagram. Okay. So this guy basically has two forces on him that I'm going to draw on this diagram. What's one force on this guy? His weight. Yeah, his weight straight down. Okay, so I'll label that mg. Okay. Okay, so it's probably 200 pounds. Let's just call it 200 newtons. Okay. Maybe it's like a little tiny leprechaun or something. So 200 newtons. Okay. But if that was the only force, wouldn't he be in free fall? Okay. So what other force is acting on this guy? Normal force. Okay. And if he's accelerating upward, then which force is bigger? The normal force up or his weight down? Yeah, the normal force up. So there is a net force on it. Okay, so this is the normal force. Okay. And that we'll call 220 newtons. Something like that. Okay. And I want to know what is this guy's acceleration. So what is the acceleration? What's the acceleration? Okay. Here, let's call gravity equal to 10 meters per second squared. Right, so say this little stuff here. Right. And if that's true, can you guys calculate this guy's mass? What is this guy's mass equal to? Like if m times g is 200 and g is 10, then what is m equal to? Like 20? Is it? You guys see it's 20 kilograms? Okay. So have like a 20 kilogram little electron right here. Okay. So 20 kilograms. Okay. Weighs 200 newtons. The scale rating is showing 220 newtons. Okay. There's enough information here we can figure out what's the acceleration. But we have to go through Newton's second law of motion. Where's okay? Right. So that Newton's law is right here. Newton's second law of motion. So the target question is what's the acceleration? Isn't acceleration net force acting on mass? Just like that? Yeah. So that's exactly what we need to solve this. So let's go here. The acceleration is going to be net force acting on mass. Just like that. Right? And then, guys, what is the net force on this guy? What is the net force? Anybody see it? Yeah, 20 newtons, right? Isn't it just the difference between these two? 220 newtons pushing them up, 200 newtons pulling them down. Is that a 20 Newton net force? Acting on how much mass? 20 kilograms. Okay. Oh, well, if you have 20 Newton net force acting on 20 kilograms, then what's the acceleration? 1 meter per second squared upward. Okay. So that's it. 1 meter per second squared. You guys good? You could also go the other way with that. So if you were told if you told the acceleration is 1 meter per second squared, you could predict that this guy's tangent scale would show 220 newtons, right? And that's more like what this is right here. Right? So G plus A. Guys, what's 10 plus 1? 11 times 20 would be 220, wouldn't it? Right? No, it's showing like tension force as a tension and elevator cable, but it's the same idea. Right? Ooh, guys, what if you were accelerating down? Do you think the difference is you would just sort of be able to subtract off the acceleration? Because you're going in like partial free fall, wouldn't you? Right? Hey, what about this? What if you cut the elevator cable? What would it feel like inside that elevator? Free fall. Would you be just floating around? And if you were standing on the scale, what would the scale read? Zero. Right? It shows here. This is all zero. Right? And A is equal to G down because you're in free fall. G minus G is zero. Do you guys see that? You see how it all comes together? All right. So last thing today. Here, I'll play a Paul Hewitt video for you guys, and then that'll be a wrap on the week.
Where's the ball? Hold it up here. The ball is hanging. Now what I'm going to do is I'm going to pull this string, bam, 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 harder, until either this string or the string's going to break. Which one do you think will break? I'm pulling that down. Don't I exert a tension in the string? Doesn't the string get tight? Huh? Wang, huh? Doesn't this one get tight too? And so I have a tension here. I also have a tension here. The string is stretched out. So as I pull gradually, which one's going to break, gang? Top or bottom? I'm going to say the top because I got another string here for the next trial. Let's watch this. It was the top. Because of the weight of the ball or because of the inertia of the ball? Check your neighbor and see if your neighbor sees which of the two properties, weight or inertia, made the top string break. Go. Why did the top string break? Because the weight of the ball is acting up here too. So the weight of the ball pulls on the top. The weight doesn't act on the bottom string. So I've got the weight of the ball pulling on the top string and the tension with which I pull on the top string. Both these, quick, boom, it breaks. But how about now I take this string and I whip it down quickly like that. Why did the bottom string break? Because of the inertia of the ball or because of the weight of the ball? Check your neighbor. I can show you that with this elastic gang. This elastic. If I pull, I can pull. Look how much that thing's stretching. Okay, but let's suppose I just go like this. Notice that? There was not as much force up here. The elastic didn't stretch as much when I pulled quickly. That force was not transmitted up here. The inertia of that ball, it wants to sit right there, huh? And I pull, it stays right there. Another word for inertia is lazy. Okay? The ball is lazy. It tends to stay doing what it's doing. Isn't that neat?
Oh yeah, that is pretty neat. All right, that's a wrap on the week.